At 46.5 billion light-years away, the edge of the observable universe sits far beyond the reach of standard human travel. The speed of light creates a boundary that physics suggests is impassable within a single lifetime. However, a specific mathematical loophole exists for any object capable of maintaining continuous forward momentum through the vacuum. Relativity allows a traveler to cross that multi-billion light-year gap in just 32.25 years of ship time. While the distance is vast, the traveler's internal clock follows a different set of rules. This relies on the ship maintaining a constant acceleration of 1.5 g's, slightly more than the gravity we feel on Earth, sustained indefinitely. As the ship approaches light speed, time dilation begins to compound. Much like interest in a bank account, the effect builds on itself, slowing the passage of time for the traveler relative to the rest of the universe. Understanding this journey requires analyzing three distinct frameworks: the exponential curve of time dilation, the mass penalty of deceleration, and the geometry of stellar networks. Energy scaling laws and mathematical compromises set the bounds for intergalactic travel, overrunning the traditional limits of a human lifespan. We model this by establishing a baseline trip to Alpha Centauri at a constant 1.5 g acceleration. By the midpoint, temporal drift is significant. Only 1.5 years pass for the traveler, while Earth observers have waited over 2.5 years. This divergence happens because velocity is finite, but time dilation is not. As velocity hits the ceiling of light speed, time dilation curves sharply upward. Every year of acceleration doubles the dilation factor. We add 9s to our velocity, and localized time slows infinitely. For the traveler, this manifests as physical compression. High velocities cause the universe ahead to flatten. On this compressed map, immense distances become negligible. Betelgeuse takes 8.5 years to reach. The Orion Nebula is 1,000 light-years further, but their data points are nearly touching. Due to extreme compression, that extra 1,000 light-year gap only adds 1 year. The traveler arrives at the Orion Nebula in just 9.5 localized years. This scaling applies to other galaxies. Andromeda is 2.5 million light-years away, yet reachable in under 20 years from the ship's perspective. At the theoretical limit, the edge of the observable universe, the traveler ages only 32 years, while 46.5 billion years elapse on Earth. Constant acceleration uses relativity to collapse distances, making intergalactic journeys survivable at the cost of the traveler's connection to Earth. Sustaining this acceleration requires converting matter directly into energy. Using the mass-energy equivalence of E equals mc squared, the fuel requirements are staggering. Reaching the edge of the universe requires the ship to consume 500 sextillion tons of matter, equivalent to the mass of 87 Earths. This 20-to-1 ratio represents the upper limit of modern aerospace engineering. For every kilogram of ship, we need 20 kilograms of fuel. Early drafts of Project Hail Mary by Andy Weir used this 20-to-1 ratio to reach Tau Ceti, mirroring modern rocket logic. However, that calculation only accounts for a flyby. It covers the energy to accelerate, but leaves no fuel to slow down upon arrival. Deceleration requires carrying fuel to slow down the unused fuel. This squares the mass requirement, turning a 20-to-1 ratio into a 400-to-1 engineering impossibility. Constant acceleration creates a deceleration trap, where the energy cost of stopping at relativistic speeds exceeds the physical capacity to carry the fuel. Solving the mass problem requires unpowered flight. This coast phase is a deliberate interruption of acceleration, allowing the ship to cover distance without burning fuel. The travel profile shifts into an initial burn, a long drift, and a final burn. Coasting 85% of the trip reduces fuel, but takes 6.8 years. A 50% coast drops time to 4.2 years, requiring a plausible 124-to-1 mass ratio. The physics of deceleration demand compromise. We trade the continuous speed of constant acceleration for the sheer efficiency of the coast phase. These spatial constraints also apply to biological systems, like a cosmic energy pathogen moving between stars. For the astrophage, the organism has a fixed survival range of 8 light-years per jump. Analyzing our galactic neighborhood reveals how far a pathogen could spread. Drawing 8 light-year spheres around stars show overlapping contiguous pathways. ATHYG data confirms 90% of local stars have neighbors within this range, creating a dense, interconnected network. The dense geometric topology of the galaxy ensures that any organism capable of an 8 light-year jump will eventually achieve universal propagation. Our models show 3 distinct forces at work: exponential time dilation, the squaring of mass ratios during deceleration, and the interconnected web of stellar networks. These boundaries scale from the engineering of a single ship to the propagation of a biological plague. They represent the immutable architecture of our universe. Accessing the stars relies on the precise application of these mathematical compromises rather than the subversion of physical laws. Internalizing these mechanics of compounding exponentials and orbital mass requires active engagement with the data. Brilliant provides the tools to work through these physical and mathematical concepts directly. Courses at Brilliant are developed by world-class educators to move beyond passive observation, using interactive modules to build a deeper understanding of STEM fields. You can explore their full library with a 30-day free trial by visiting the link on screen or in the description. That same link also provides a 20% discount on an annual premium subscription for viewers of this channel. Master the math, and the architecture of the physical universe becomes much clearer.